Children's Calibration of Reaching Estimates in Virtual Reality, presented by Sarah Creamer-Gear. Every day we make judgments about our ability to interact with objects. For example, these images depict a child who must decide whether or not they can reach up to a book on a shelf or reach out to grab a book on the desk. This decision depends both on the information in the environment, such as the height of the shelf or a distance of the book, and the individual's body dimensions, such as height and arm length. These opportunities for action that are dependent on both the environment and our body size or capabilities are called affordances. What's particularly interesting about children is that their capabilities for action are changing relatively quickly compared to adults because of rapid changes in body size. Children have experience adapting to their changing body as they grow and act in the world, and studies in the real world show that children as young as 14 months old adjust their actions for changing circumstances, such as when crawling on sloped surfaces. Across a number of real-world studies, children are shown to perceive affordances for action scaled to their bodies, but their performance is different than adults. They generally improve with increasing age over childhood, both in their accuracy of perceived affordances relative to their actual capabilities and in their calibration or response to corrective feedback. Studies in VR have examined a range of affordances, including navigating through openings, extending one's reach, grasping objects, crossing gaps, stepping over obstacles, and determining if a surface is suitable for standing. Understanding affordances in VR is critical for improving user interaction for numerous applications, but the study so far has been mostly limited to adults. Our focus is on reaching judgments, and specifically how biases and estimates in reachability can be addressed by providing feedback about action outcomes in VR in both children and adults. A number of studies have shown that interacting with the environment and receiving feedback in different forms can calibrate affordance judgments to be more accurate. By accurate, we mean calibrating the perception of action capabilities to be more similar to actual capabilities. Most often, feedback comes in the form of action outcome feedback, where, for example, in a reaching task, a user might reach and then see feedback from an avatar arm about how far their reach extends. However, other forms of feedback can also be effective, such as verbal correction or general movement through an environment. In Gagnon et al., we showed with adults that participants' judgments of their capabilities to reach out horizontally were largely overestimated, but could be calibrated with feedback from seeing the position of a virtual controller in the environment after they reached. So this leads us to the question of the current study. Do children calibrate reaching estimates in VR as adults do? We extended our work on reaching out and reaching up affordances to directly compare children and adults in their accuracy and calibration. Our first question asked, how are reaching out and reaching up affordances perceived by children and adults? Based on prior work, we expected the horizontal reaching out estimate to be overestimated compared to reaching up. And further, we predicted that adults would be initially more accurate than children in their estimates. Second, we asked whether reaching estimates would calibrate with feedback from actual actions in the virtual environment. We predicted that both age groups would show calibration of actions and show greater accuracy as they progress through the task with feedback. Given the larger predicted error in reaching out versus up, we predicted that reaching out would show greater calibration effects. And finally, we predicted age differences, where adults would recalibrate their reaching out judgment at a faster rate than children. Our study included 18 children aged 8 to 13 and 22 adults aged 18 to 30. The participants experienced the Great Hall from Harry Potter as a virtual environment in the HTC Vive Pro. We had a within-subject design where participants experienced reaching up and reaching out affordance judgments. In the reaching up affordance, participants made judgments on whether they could reach up vertically to a floating broomstick. In the reaching out affordance, they made judgments on whether they could reach out horizontally to a Harry Potter snitch, which is a golden spherical object. For each affordance, participants completed two types of trials. In adjustment trials, participants adjusted the object by pressing a button on the controller while keeping their arms at their sides until they thought it was at the distance that they would just barely be able to reach. In feedback trials, they were presented with the object at a specific distance. They made a verbal judgment on whether or not they could reach the object. Then they actually reached out or up to receive visual motor feedback on the accuracy of their judgment. The visual feedback they received was provided by seeing the Vive controller in VR as they physically made their reach. Here you can see the adjustment phase where participants adjusted the broom's position to what they perceived to be just reachable. They repeated the adjustment trial 2 times, one starting above their baseline capability and one starting below. In the feedback phase, participants made a yes or no response about whether they could reach the broom before then reaching up to see if they were correct or not by the placement of the controller. Trials progressed in blocks. Participants made 2 initial adjustment trials in block 0, setting the broom or snitch to their just reachable location, which we considered their baseline reach judgment. In each subsequent block, they performed 2 feedback trials at different percentages of their actual reach, such that one trial was farther than their reach and one was closer. Then they completed 2 more adjustment trials. Our primary measure was their affordance ratio, which took the average of the 2 adjustment trials at each block and divided this by the participant's actual reach, which was measured in VR at the beginning of the experiment. A ratio of 1 would indicate that they set the object exactly at their actual reach. A ratio less than 1 indicates underestimation of reachability, and a ratio greater than 1 indicates overestimation of reachability. We conducted a repeated measures ANOVA to investigate how ratios changed with affordance type and feedback across blocks, including age group as a between subjects factor. Here I show the average affordance ratio on the y-axis and block number on the x-axis. Reaching out is presented in blue and reaching up is presented in red. Adults are the solid lines and children are the dotted lines. The 1.0 line represents an average adjustment that exactly matches actual reach. So what did we find? First, as predicted, reaching out was overestimated more than reaching up for both age groups. Supporting our second hypothesis, children overestimated their abilities for reach affordances, for both affordances more than adults. Supporting our third hypothesis, we found calibration of judgments in both age groups. The ratios decrease and become closer to our accuracy line of 1 as feedback blocks progress. Fourth, as we expected, there was a different effect of block for reaching out versus up. We saw a significant decrease in ratios from block 0 to 1 and block 1 to 2 for reaching out, but only from block 0 to 1 for reaching up, supporting greater change for reaching out. And finally, we did not find support for hypothesis 5, that there would be a difference in the rate of calibration for children compared to adults. Both showed a similar decrease in affordance ratios across blocks. To conclude, this is the first study that assesses calibration of children's perceived affordances in VR. We focused on reaching as a critical component of interaction in VR that has been studied in adults but lacked an investigation in children. We found predicted differences in affordance estimations in children that are consistent with some real and virtual world studies showing more overestimation or less accuracy in children. And further, we established that children do calibrate their perception of reachability when provided with feedback in VR. These findings are important for guiding future use and applications of VR in areas of training, education, and safety in children. I would like to recognize my co-authors, notably Hunter Finney, the first author of this work, and our funding support.